Okay, so hi, we're going to be doing optimization problems, and so for my simple example, I'm going to have a fence problem, which is shown below. And for my complex example, we're going to do what point will maximize the area, so this will be on a graph. But typically with optimization, it's in the name. When you see a problem that's asking you to maximize or minimize something, you know that you're going to have to use these steps to optimize your total value. So typically, it's a maximize question, which includes area, which is the equation we have below, surface area, volume, or distance. And then sometimes you'll see a minimize, and the most common minimize question is cost. So we did a problem like this in Unit 3, where it was like a soda can, and the company wanted to maximize the volume that would fit inside of the can, while minimizing the surface area and cost of this. So here we have to do both surface area and volume and figure out like what would minimize cost while maximizing the volume. So down here, our simple equation is a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. What are the dimensions of the field that has the largest area? So I got this question from Coins Math, and so typically when you see a problem like this, it's really easy to get caught up in the details, so I would like you to follow a step-by-step guide. So first, we're going to figure out what are the givens in our problem. So here, we have a value right here, so we're going to do total feet is equal to 2,400. That's how much we can use to fence off this field. And so what are the dimensions of the field that has the largest area? So the question's asking you for largest area, so we know we're going to have to maximize area. And so from here, you want to draw out a diagram. You can skip this step if it's a simpler question, but with more complex questions, it's much easier if you try drawing stuff out so you can figure out, oh, like, I need to find the area here to figure out the volume over there. So for this question, we know that there's a river, so let's say this blue is the river here, and we have a rectangular field. So it's going to be rectangular. These two sides are going to be the same, and then there's going to be that side. So let's say our width is x, and our length is y. So from here, we can kind of see that the x and y's are our perimeter, right? So by visualizing this, we know now what formulas we're going to be able to use. So 2,400 feet was our total number of feet, is equal to 2x plus y, because this is our fencing right here, and we know we have this many feet. And now the other thing with our given was we need to maximize area, so we can put the area function, the area formula here, which is going to be length times width, and your length is our x, so we can rewrite this as x times y. Okay. Now, typically we would solve for something, right? But our issue is we have two variables and we don't know the value of either. So in order to figure out the value of one of these, we're going to have to write one of these equations in terms of another variable. So when you look at this, you see that the perimeter function has a numerical value, right? While the area doesn't. You can't really solve anything with the area. Even if you try to rewrite this, it's not going to work. So we're going to use the perimeter equation and we're going to rearrange. So our fourth step is rearrange for a variable. So here we're going to take our perimeter function and we're just going to simply rearrange. I like to rearrange and solve for y's because typically I just gravitate more towards the y, but you can do whatever's easier. Sometimes just looking at the equation, one is going to be easier to solve for than the other. So for this equation, 2,400 minus 2x, we're just rearranging, equals to y. And now we know what y is. So we can plug this back into our area function. So area is equal to x times 2,400 minus 2x. Make sure to put the parentheses around. So before we had x times y, right? Now we substituted this down here. And so now we can expand out. Area equals to 2,400x minus 2x squared. And if you remember from our first unit, when we have an equation like this with our x's, we can figure out the first derivative to find critical points, or our zeros, right? So if we figure out the derivative of this, we can use the power rule. So 2,400 x to the power of 1, you take your exponent, multiply it by your coefficient, it's going to be 2,000, and then you do your exponent minus 1, so that's just going to be x to the power of 0, which is 1. And then here, you do the same thing, 2 times 2, 4, x minus 1, it's just going to be x. So now we can solve for our x value by setting this equation equal to 0, right? Now I'm going to rearrange. Negative 4x equals to 2,000. Positive, because we're doing the opposite as we rearrange. Divided by 4, x is going to be equal to 600. So now that we have our x value, we go back to the question. What does the question ask us again? What are the dimensions? So that means we need both our x and our y. We've solved for our x, which means we can now plug this x value back into our formulas we wrote over here to figure out our y, right? So now the fifth step is going to be plug in for other variable. This can vary from question to question because sometimes it's only going to ask you for one dimension, sometimes it'll ask you for both, sometimes it'll ask you for the area or the surface area or the volume. So now we're going to figure out the other value. So 2,400 equals to 2 times 600. We solved for that. Plus 1. So this is going to be 1,200 equals 2,400 plus y minus 1,200 minus 1,200 is going to be 100 is equal to y. So now we have both of our values. We know this is our y value and we know this is our x value. And we can go back to our equation. The dimension we were given here is in feet. So we're going to go back to our equation and make sure we have our units. Always double check, because when you're doing the math, like over here, our formulas aren't going to have the units, but our final answers need to have the units. So that was a simple example, and we're going to use the same method to solve a complex. Okay, so now for the complex problem. So this one's on a graph, and the graph was given to us. This is from my open math, and we're going to use the same process. I rewrote it up here, but we're going to do this with this problem. So the problem reads, a rectangle is constructed under the graph of f of x equals x squared plus 15 with one corner at 10, 0 and one corner on the graph f of x equals x squared plus 15, where x is greater than or equal to 0, but less than or equal to 10. Find the x value that will maximize the area and approximate to 3 decimal points. So, number 1, we are going to write our givens. So we know that the function is going to be f of x equals x squared plus 15. We also know that the rectangle is under, so the visualization helps. And so we can also skip step 2, but since we have the graph here, I'm not going to write that out. And then corner 1 is going to be 10, 0, so on the graph here. And then the other corner is at some point x, f of x. And so now we need to find max area and x value. So because we have this diagram, I'm going to just pull this instead of drawing it, since we're given it to us. I'm just going to move this down and just make it slightly bigger. So this will be our step 2 diagram. Now step 3, formulas. So we know that we need to figure out the width times the height. That will get us area max. So how are we going to figure out the width and height of this equation? So to start off, this height here we know is actually going to be f of x. And so if that height is f of x, we can go back to our f of x equation because we know what f of x is. And for height, we can actually just plug in this equation here. So this should be a plus. And now for width. What is our width here? So this 10, 0 doesn't give us the whole width because this rectangle doesn't go all the way down to the origin. But we know that whatever this x value is, we can just subtract it from this 10 to figure out the value of this, because if this whole thing is 10, and this part right here is x, 10 minus x will give us the value of just this section. So here, for width, we can do 10 minus x. And now we know what the area max is, right? So this diagram actually really helped us out a lot. The whole complex part of this was visualizing this and figuring out what our width and our height was. So now we can rearrange. And in this case, since we have our x, since both of these are our x values, we don't have to rearrange or solve for one variable. We can just expand this out. So using this box strategy, because I just find this much simpler. 10 minus x, so this is going to be 10x squared. This is going to be negative x cubed. This is going to be 150. This is going to be negative 15x. And then we can write this as negative x cubed plus 10x squared minus 15x plus 150 is equal to area max. Let me switch. And so now we are finding our critical values. So like we did with the previous equation, we can figure out the derivative of this to figure out what our zeros are. So same thing, we're going to use the power rule. Exponent is 3, so negative 1 times 3 is going to be negative 3x squared. And then 10 times 2 plus 20 minus 1x. And then 15x, negative 15x is just going to be negative 50. And then 150 is just times 1. So this is our equation. And now we set this equal to 0 to solve for the value of x. So here, since we have a negative, we can just divide this whole thing by negative 1 just to make it simpler. Minus 20x plus 15 is equal to 0. And this is a Calc OK problem, so I would, from then, just insert this derivative. But make sure you put all of the values, or all of the work, because you won't get the points otherwise. But if I plug this into the calculator, we're going to get x equals to 20 plus or minus square root of 220 over 6. And so x is equal to 5.805, or x is equal to 0.861 are our two values that we get. And so we need to figure out which value is going to give us a max area. And so to verify this, we are actually going to do this plug-in step here. So step 5 is going to be to verify the maximums. So we're going to take this and we're going to do 10 minus 0.861 times 0.861 squared plus 15. We're going to plug this into our calculator, and this is going to get you approximately 9.139. We're going to do the same thing with x equals 5.805. So 10 minus 5.805 times 5.805 squared plus 15, which is going to be approximately 204.3. So this step is just calculator based. We're just plugging it into this equation like we did for the first problem. And so because this value is greater, we know that the value of x that would maximize the area is going to be equal to 5.805. So that's it for this equation, for this problem. Okay, and so I want to end off with reminding you that if you follow these steps, any complex problem will be much easier, especially if you do the diagram. And here are my sources. Thank you for watching, and I hope this helped.